Imagine this. A car drives 120 miles in 2.5 hours. We could easily calculate the average speed for this car by taking the total distance over the total time. 120 miles over 2.5 hours. The average speed then would be 48 miles per hour. But does this mean that the car was going 48 miles each hour it drove? No. People stopped for snacks, bathroom breaks, etc. What if in that same problem we wanted to find out the car speed at exactly 45 minutes? Well, we could graph the car speed on a position time graph. We know 2 points, the first being 0, 0, and the second being 2.5, 250. We also know a slope, 48. The slope is the speed because speed is distance over time, distance being y and time being x. So the function is y is equal to 48x. So if we wanted to find the speed of the car at exactly 45 minutes, it would be fairly easy. All we have to do is find the slope of the line because slope is speed. Say that we kick a ball with a speed of 8 meters per second. The ball is affected by gravity as it's kicked through the air, so it reaches a peak and then turns back around. It has a parabolic shape, thus it has a quadratic function. The function for this ball is y is equal to 4.9t squared plus 8t. We could calculate the average speed for this function as well, the same way we calculated the car's average speed, but it would end up being 0 because the initial and final distance are also 0. So what if we wanted to find the speed of the ball at exactly 1 second? This one would be a little bit harder because it's a curve, not a line. The slope is not consistent. So how do we find the speed? Well, we could try using the same formula we have been using, but using different intervals. We could continue to make the interval smaller and smaller and smaller until it ultimately reached x equals 1. But once it reaches x equals 1, the formula is no longer possible because the distance will be 0 and the time will also be 0. Division by 0 is not possible. So how do we solve this problem? And it can be solved using limits. In this parabola, say that we want to find the slope at exactly x equals 3. The slope at x equals 3 would be a tangent line. But the first problem that arises is that we cannot create a line with only one point, but we can approximate one using limits and secant lines. If you were to continue taking 2 points, approaching our point, x equals 3, until you were practically at our point, then you could approximate the true tangent line because the secant line has such a small difference from our desired point. Using secant lines is using limits. A limit means that as x approaches a, f of x gets arbitrarily close to L but could never equal L, which is exactly what our secant lines did. They approached 3 but never equaled 3. It gave us an approximation, which is all we can do. Thank you. This has been the tangent line problem.